All right, so we've derived the Fife equation, basically the equation that governs the current and the voltage waveforms across my inductor as I apply an input in an RL circuit, okay? And so what I want to do just real briefly is I want to take this equation and I want to take it into the next slide with us. And I want to break down the two cases similarly to what we did for RC circuits. I didn't have a slide prepared for this, so that's why this slide is blank, but I think it's important. And so in the RC circuit case, we broke it down into two cases. We had the charging case and the discharging case. Well, we don't really say charging and discharging for inductors. More likely you'll hear that the coil was energized or de-energized, and so I'll stick with that terminology because that's what I've heard more frequently. I don't think it's common to say charging or discharging. Okay, and so in the case where we're energizing the coil, right, that would be the case where I have my voltage source here, my switch is open, my resistor and my inductor. And if we recall, well, I said that the current in an inductor cannot change instantaneously. So the initial condition here would be that the current through the inductor at time t equals 0 is 0. And so that means that there's initially no current flowing in the inductor, which is clear by the fact that this switch is open, right? Well, when I close that switch, right, at some time, probably time t equals 0, I'm going to close that switch. And what's going to happen is my current is going to start ramping up just like my voltage did in my RC circuit. That's the behavior that is described by this equation up here. Okay? And so if I can sit here and reason about this, and I know that my initial current was 0, then I can take the Fife equation here, just as it is. Hopefully I don't grab the box. I grabbed the box too. That's okay. And what I can do is I can notice that in the energizing case, then my initial current is 0, so this goes to 0. And what I'm left with is IL of t is equal to the final current, which is going to be once this transient behavior has passed and my inductor is now a short. Again, it's going to just be whatever VI, this will be 0 volts, and then my current final is going to be VI over R at that point. But I'll just write it as ILF for now. I can factor out an ILF, and I get that ILF times 1 minus e to the minus t over L over R is going to be my expression for the energizing of the coil case, okay? And then how about de-energizing the coil? What might that look like? Well, that might look like I've got some, let's say I've got my inductor here, and then I've got a resistor, and I've got, let's say I've got a current source sitting here pumping current into that inductor, and then at some time my switch is going to open. And when it does open, it's going to connect over to ground here. All right. So I've got current flowing in my inductor, and let's say that this is ILI. That's the value of my initial current. And I know that my final current is going to be 0. Okay? And so what I do is I pull my Fife equation in. And my final current is going to be 0 because it's going to just all the energy that's stored in my inductor is basically going to burn up as heat in my resistor, and I'm going to be left with no energy once I open that switch over to the ground side. Okay, so maybe it's not clear what's happening. I'm saying I've got a current source that's feeding current into my inductor, a constant amount of current, and since it's constant, the voltage across the inductor is 0. And I'll basically be sitting at some current, and then once I switch over to this ground, the current's no longer connected, and so the inductor de-energizes, and we get this discharging behavior, or de-energizing behavior, if you will. And the behavior is described by this equation where my final current is 0, so both of these go away, and my IL of t is going to be equal to IL initial times e to the minus t over L over R. All right, and so that is my energizing case and my de-energizing case. Just wanted to break those down just to show you how similar this really is to RC circuits, that the equations are almost the exact same, except we're talking about currents instead of voltages, okay? And so in the next video, I'm going to go ahead and solve an example where we are energizing the coil, all right?